Okay. Says we're live. I believe it. Right, okay. Previous chapter 4 of the compiler book. Conditionals. The previous chapter was rather mechanic in that once we knew how to add one operator to, it's a bit loud in my head, to a monkey implementation, we could follow the same recipe for the others. In this chapter, though, we're going to take it up a notch. One more. Yeah, the last one was as soon as you did it's fucking awesome when nobody's here yet. We need to answer, yeah, the last sections. Once you saw the pattern for one, you could just do them all. Quite mechanical. Yeah, still fun. Made me feel like I knew what I was doing, which is always a good boost. We need to answer a very concrete question. How do we get our VM to execute different bytecode instructions based on a condition? I guess we only compile? No, it's a compile time known value. Interesting. Well, by adding only the section. Well, okay. I think it would be if by controlling what's on the stack. As we'll see, there's a number of small puzzles hiding behind this question, and solving them is great fun. Especially once we get down to the nitty gritty. Wonder who they are. Before we do that though, we have to answer this question without writing any code. So let's give this question a little bit of context and frame it. Monkey's conditional oh, sorry. look like this. If that, everything's fine, else laws of universe broken. In which case, everything's different. If the condition evaluates to a truthy value, the first branch is executed. Correct. That's a good point, really. I feel like the complexity is just coming. What I did so far was just like a walk in the park. Anyway, that's the branch containing everything is fine. If the condition is not truthy, it's executed. The first branch is called the consequence, and the else is called the alternative of a conditional. In order to provide for a possible implementation of conditionals and to refreshen, is it German? Refreshen dein memory. Let me go over the implementation of conditionals in writing an interpreter in Go real quick. When we come across an AST.if expression in the evaluator package's eval function, we evaluate its condition and check the result with the isTruth function. Right. In case the value is truthy, don't like, in my language, it's not going to be truthy. It's only true or false, booleans only. Don't like that truthy. It's quite confusing, really, in the languages that I've used. It's not confusing, but it's not explicit. I like explicit stuff. We eval the consequence of the AST.if expression. If it's not truthy and the AST.if expression has an alternative, we eval that instead. Why return a null? Excuse me. Shouldn't it just carry on with the rest of the statements? Now I gotta have a look. Let me zoom in a little bit. Is that readable? Yeah, that's fine. That's the book. Yeah. Thing AST if expression. Right, I don't think I think it's a bit too zoomed in. That's still, yeah, that's still readable. Yeah, I can read it. Okay, and let's go to parse if, yeah. Right. Yeah, don't remember returning null. Weird. Ah, okay. You mean, okay, I think I understand. But the alternative itself is going to be null. Like here. No, but that's object. Okay, never mind. Let's keep going. All in all, implementing conditionals took us only around 50 lines of code. You mean the eval? Yeah, because this is just the parser. And the reason why it was so easy to implement was that we had the AST nodes on our hands. We could decide which side of the AST if expression to evaluate because we had both available to us in the evaluator. Right. That's not the case anymore. Instead of walking down the AST and executing it at the same time, we now turn the AST into bytecode and flatten it. Oh yeah, fuck, that's a good point. I didn't think about that at all. Yeah, and then when we create the bytecode, we don't know. We only have the index of the pointer to the stack. Yeah, we don't know the value because it's compile time or comp time. I mean, not comp time, compile time. We've got to fix the camera. It's a bit too bright. I just realized I'm in the corner. That's fine. It's not a big deal. Flatten because bytecode is a sequence of instructions and there are no child nodes we can choose to walk down or not. Yeah, exactly. I didn't think of that. It's not that easy. Interesting. Interesting. That brings us back to the hidden main question of this chapter and another problem we have to solve. Yeah, actually, this had the same question: how to represent conditionals in bytecode. Let's say we have the following code. Yep. Okay. We already know how to represent the condition in bytecode. Yep. So we push two objects to the stack, push the operator, and yeah, that's it. Because we just did it yesterday. Okay, yeah. Interesting. Yeah, we can represent this. Easy. So all you gotta know is what to do with this and then which one of these to execute. Oh, actually, I think I got it. Because you'll execute this, there'll be an opcode for, let's say, if you see if you gotta evaluate this condition, and then you'll push a boolean onto the stack, or maybe either a boolean or another opcode that says to skip one. Maybe. I think whatever this operand is will need opcode is, it'll need an operand. Yeah. Okay. I mean, that's one idea. It's very error prone, but let's see. But how to tell the machine to either execute the one part or the other part, depending on the result of the op greater than instruction. Yep. Well, I think it would be using an opcode. Let's see. If we were to take these instructions and pass them to the VM as a flat sequence, what would happen? VM would execute all of them. Yeah, exactly. You would sort of skip over one of these based on these. Then at the end of constant up greater than, after the end of this thing executing, it depends what you push to the stack, what opcode. Okay. Instruction pointer, fetching, decoding, and executing without a care in the world. No decisions or branches inside. That is exactly what we don't want. Excuse me. What we want is for the VM to either execute the op add instruction or the op sub instruction. But since we do pass bytecode around as a flat sequence of instructions, how do we do that? With opcode. Or you could turn it back into a tree. Could sort of unflatten it. Seems like a lot of work though. For a conditional. Oh, or is this like where what go to statements? So you'd say go to stack pointer this. Huh. I think that might be it. I'm a fucking genius sometimes. Well, we reordered the graph of instructions so that it represents a flat sequence of instructions. The question becomes this. Yeah, what do we fill in the blanks? I do have to say, I like how he breaks the problem down. Because this is the bit that I struggle with. I can solve a problem. Can't seem to break him down very well yet. That's pretty cool. That's pretty nice. Okay. Excuse me. We need to put something in the blanks so that based on the result of greater than instruction, the VM either ignores the instructions of the consequence or the instructions making the alternative. It should skip them. But instead of skip, should we say jump over? I knew it. I fucking knew it. Jumps are instructions that tell machines to jump to other instructions. They're used to implement branching in machine code. Okay, giving them the name branch instructions. And with machine code, I mean the code that computers execute, but also the bytecode virtual machines run on. Okay, yeah. Translated into the technical terms of our VM, jumps are instructions that tell the VM to change its instruction pointer to a certain value. Yeah. Okay, so if you see a jump statement, you check, you pop the last value, and based on that, you make the decision. Oh no, because hang on, feel like it's still fucking zoomed too much in. Is that still fine? But yep. So it's going to be what's the name? Executed somewhere here. Actually, no. Okay. Translate? Yeah, that's a good question. Oh, I guess you would save. No. Because you don't know how many instructions in the block. How would you know without... I guess it doesn't matter. Because... kind of does. That's interesting. I mean, before I read the answer, I want to at least try. If expression is that if expression need that yet so you'd the function's recursive too. So we have consequence. No. We have condition. Alternative. And alternative can also, but I guess that's, yeah, I think it'll be solved recursively, as in if there's more condition here, because this could also be like else if. So this would parse let's say this is an infix. And then it adds some bytecode. No, sorry. Constant. Hang on. SP. SP is just stack pointer. And then opcode. Yeah, and then it'll come back. Need to add jump. Or but how do we know? Oh yeah, okay. Hang on. So we know jump start, right? We can save this and then we create the bytecode for consequence, which could be, yeah, SP, a lot of SPs, because can have multiple statements, and on, and then yeah, and then okay, why am I making this so complicated? Okay, so this would be jump 1 and then 2. Will be stack pointer plus 1. Same here, plus 1. Because the next statement is the start of the consequence. Yeah, and then you can just call make on this. that would bytecode SP. Yeah. Okay. Doesn't seem that bad now. Actually, this can just be it's one true. Yeah. Oh, but hang on. It needs two. Because you need to know what the second jump point is. Not that straightforward. Or at least the way I'm trying to do it. Hang on, what does make return? Sorry, emit. Takes an operator and operand. What else? What does it do? Grabs the constants, makes the new instructions, and appends the new instructions. So that means somehow we need to or we have to go back. That was weird. Yeah, or yeah. Or we do this ahead of time, make it O1, and then after this, we know what the next pointer is. We just update. Something like that. That just sounds unnecessarily complex. Okay. I mean, it's not the best solution. Let's have a look what he says. Jumps are instructions that tell machines to jump to other instructions. They're used to implement branching in machine code. Giving them the name branch instructions. With machine code, I mean the code that computers execute, but also the bytecode virtual machines run on. Yep. Translated into technical terms of our VM, jumps are instructions that tell the VM to change its instruction pointer to a certain value. Excuse me. Here's how that works. Let's say, hypothetically speaking, that we had two jump opcodes and call them jump if not true and jump no matter what, the eventual. statement. I don't know if that's really correct. Because if it's not true, you can also just continue. Okay, get it. If there's no else, got it. And that's correct. You could use them to fill in the blanks in a graph from above like this. When the VM executes these instructions sequentially, I think this part I get. But then I'm just stuck on the detail of how. Yeah, I think this is fine. Yeah. Here's where it gets interesting. After executing the consequence of the conditional, it would increment its instruction pointer and start to fetch, decode, and execute the next instruction. Op constant 2. There's actually another problem, which I just realized. Ah, fuck. There's actually a simpler way. So here, I just need to know if I need to make the jump. I don't need 2 jump points. Not now, pop. Yeah, so the question then becomes, oops, sorry. Fuck. Okay, not too sure yet. And this one is also fine. Because we ever get to here, oh no. Actually, if we can do this one's not bad. Right, okay. The next instruction. Condition ending with op greater than instruction. That results in a boolean sitting on the stack, just as we defined and implemented it in the previous chapter. The next instruction, jump if not true, would tell the VM to jump to op constant for instruction. Excuse me. Only if the boolean on the stack is not true. Yes, correct. That's the case. The VM would jump over the consequence and write to the else part of the conditional, the alternative. Yeah. I think I'm just thinking about the how. I get this bit. I think it's not too hard to understand. And in case the boolean on the stack is yeah. Constant 2 and start the consequence. Yeah, I think this one is the consequence is easy. It's the alternative and the eventual jump. Here's where it gets interesting. After executing the consequence of the conditional, the three instructions that end with op add after executing the consequence of the conditional. Yeah. The VM would then come across, jump no matter what. And that's fine. That ends our little thought experiment and gives us a clear result. If we had two opcodes, like these, we could implement conditionals. But still, a last question remains. How would we represent the arrows? Exactly. My question. Oh, what's this? Yeah, how to get this 8 and 11. I would think you would update it after the fact. I mean, I think that's the only way. Yeah. Yeah, actually, what you could do is keep the pointer to this location, jump, maybe XY, and then after this, XY equals, let's say 22, whatever. Yeah, that's another option. Or we could, I mean, yeah, and we already know the pointer at this point. It's just SP -1. It's not on the stack yet though. Oh, sorry. We know it's, what's the word? Instruction pointer? Maybe. Right, okay, I think that can be done. Not a problem. Not as bad as I thought. Well, why not use numbers? Jumps are instruction that tell the VM to change the value of its instruction pointer, and the arrows in the diagram above are nothing more than potential values for instruction pointer. They can be represented as numbers contained in the jump instruction as operands, and the value being the index of the instruction the VM should jump to. Yep. That value is called an offset. Used like this, with the jump target being the index of an instruction, it's an absolute offset. Yeah, makes sense. As in, just go to this pointer. Relative offsets also exist. They're relative to the position of the jump instruction itself. Yeah, denote not where exactly to jump to, but how far to jump, right? I think either's fine. Don't understand why we need relative jumps. Because if we already know where it is, I mean, I guess it's the same. I don't know. We replace the arrows with offsets and give each instructions a unique index that's independent of its byte size. The diagram looks like this. Yep. Now it's 8, the index. Yep, correct. VM should jump in case the condition is not true. Is 11, that's the end of following the whole conditional. And that's how we're going to implement conditionals. We'll define 2 jump opcodes. One comes with a condition and one does not. They'll both have one operand, the index of the instruction where the VM should jump to. Yep. Question is, how do we get there? What do you mean? Isn't it, you mean like how to jump? Yeah, I would assume. Yeah, this is the same. Okay, I understand what he's saying. It's like, how do you get these numbers? That was the same problem I was pondering about. Save it in the compiler's recursive compile method. Having just called compile again, passing in the dot condition field of an AST if expression. Right, condition has been successfully compiled and we've emitted the translated instructions. Now we want to emit the jump instruction. Tells the VM to skip the consequence to the conditional if the value on the stack is not truthy. Which operand do we give this jump instruction? Where do we tell the VM to jump to? Don't know yet. Exactly. Since we haven't compiled the consequence or the alternative branch yet, don't know how many instructions we're going to emit, which means don't know how many instructions we have to jump over. That's the challenge. Yep, exactly. I have to admit that solving this is a lot of fun. It isn't, I agree. And a great part of the fun comes from the fact that it's pretty easy to write a test, tell the compiler exactly what's expected, and then make your way there step by step. Why do we need 2 jump instructions? Seems a bit excessive. I might try having just 1. Yep, both of them take 2 operands. Oh no, that's just the width of the operand. That makes sense because they're all 16 bits. Might try to do it with 1. I think it's quite possible. To only jump if the value on top of the stack is not truthy, i.e. no false, no null. A single operand is the offset of the instruction the VM should jump to. Yep. Op jump will tell the VM to just jump there, with there being its operand. I kind of see why he added the second one. Because if you come across this jump, you need to check the previous value on the stack or the current top of stack. Okay. But I suppose you could also just make this wider. Let's say 3. And then you add a bit that signifies it's this one. Guess it's just making it unnecessarily complex. You might as well just add an opcode. Alright, I'll think about it. Right, so for this one, what do we do with the if? Actually, don't really do anything. All we care about is this. So we'll push that to the stack, then add a jump. Jump if not true there. Then push this and then jump again. Yeah, add a jump which is to here or whatever's after. and then this. Okay, makes sense. Up, true. Yep. Constant. Yeah. Pop. Constant. Pop. Where's the second jump? Oh, because there's no else. Okay. Jeez. It's a lot of reading. It's not too bad. Once parsed, the input turns into an if expression with a condition and a consequence. The condition is the Boolean literal true, and the consequence is the integer literal 10. Both are intentionally simple monkey expressions because in this test case we do not care about the expressions themselves. We care about the jump instructions the compiler emits, that they have the correct operands. Yeah, exactly. Seven. Oh, did he just count it? 1, 2, 1, 2, 3, 4. No. 1. No. What is what? 2 and 4. 6. Okay. That makes sense. Because each number's represented by two 16-bit each number is represented by 2 bytes. That makes sense. I don't know. I think I'm confusing everybody. Okay. Exactly. We don't care about the expressions. We care about the jumps. Show the offset of the instructions generated by code.make 00 and 07. Yeah, makes sense. Are based on the numbers of the bytes each instruction makes up. Yeah, of constant takes up 3 bytes. Okay. Op takes 1 because it's just the opcode. Op constant takes itself and 2 bytes. Again, that's how wide the numbers are. That's 3, 4. Right. Where's jump? Okay, and then there's another one. This is also 4. What? That makes no sense at all. Alright, never mind. That's fine. That's just details. It'll be easier when just write the code. The first instruction we expect the compiler to emit is an up-true instruction to tell the VM to push VM.true onto the stack. That's the condition. Yep. Yep. But where does the pop instruction come from? Whoa, I didn't notice that at all. It's not part of the consequence. It's there because conditionals in Monkey are expressions. If true, 10 evaluates to 10. Yep. And standalone values, expressions whose value is unused, are wrapped in an AST.expression statement. And those we compile with an appended or pop instruction. Yep, because we don't want them staying on the stack. Because the number on its own, right? This will never be used again. Just pop it off as the end of its lifetime. Very brief. The first pop is after the whole conditional, which makes its offset the location where, yeah, and skip the consequence. Whoa. Hang on. It's 7. If you jump here, does it mean it's gonna pop this true value? Because this statement is never executed. Looks a bit sus. Not too sure. I'm more confused than before. I thought it should have come here. Oh no, hang on. Because we do need to remove that constant. Oof. It's a bit rough, man. Not sure what's happening. So now you might be wondering what the 3333 is doing in the monkey code. Serves as a point Right. Yeah. It's just a reference as to where to go. But in order to make sure that our jump offsets are correct, it helps to have one expression in the code which we can easily find among the resulting instructions. And we use a signpost that tells us where we shouldn't jump to. Right. Of course, the op constant 1 instruction. Yeah, exactly. Right. ast dot if expression compile node dot condition, which is just an expression. Okay. So the condition is added. Next, you'd add the jump with an empty value. I guess jump with 0 for now. And then compile the consequence. Yeah. Now to emit an op-chop instruction with an offset pointing right after the instructions before compiling. The answer is rather pragmatic. Yeah, hey, I guess what else can we do there? Maybe this. I was hoping for something different. Let's use a bogus offset and worry about fixing it later. And I guess we can do an assertion when we execute. And if it's, let's say, 0, you should just... Oh, no, it can't be 0. What if it's a while loop? No, even then it can't be 0. What if there's only a while loop? I don't know. Okay, never mind. Yeah, can do an assertion during execution. Yep, some value. I mean, that's not a good value because... Oh yeah, that's actually past the stack. Anyway. Oh yeah, you can just do stack length plus 1. And then you can assert that the jump is within the stack. Okay. So okay, and then you compile consequence, which would be another expression. No, it'd be a statement. So that means AST. Yep, it's a block statement. Fine. Leave that in. Yeah, so I do need to let the compiler know what to do with block statements. Might be here. Block statements. Statement. SD dot node. Okay, so it's the type of statement. This would be here. Yeah. Right. Then go ahead and execute that. And then after that's done, yep. But does it return anything? No. Yeah, no, because it's recursively calling compile. Yeah, it's pretty straightforward. For each statement, call compile. Then it's not very different to excuse me. Yep, I think the test would still fail. But besides the bogus offset, we didn't expect to magically disappear. There's a new issue visible in the output. Far more subtle one. Test instructions failed. Wrong instructions length. There is an additional op-pop instruction generated by the compiler at position 7. Its origin is the compilation of no dog consequence. Yep, that makes sense, really. An expression statement. What about the condition? We don't want that either, though. Because at some point that needs to be removed. Where is the test? Here. Right. Hope true. Where do we pop this value? Right, here. But if it is true, no, okay, got it. Because when you come to this instruction, you gotta pop the last value to see what it is. Okay, no, that makes sense. All right, fine. I was getting confused for no reason. Where was I? Think, yeah. Right. Yes, 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 yes. Didn't expect to magically disappear. It's a new issue visible in the output, far more subtle one. So it's up true, that's correct. Up jump, not truthy. How's that correct? 7. Weird. Okay. Oh, sorry, that's the want. Okay, that makes sense. Yep, up true is correct. Jump not truthy is correct. And you push the constant of the consequence. Oh yeah, why are there 2 pop? How many instructions? Just 1, right? There was just 10. Where did it go? Yeah. That's strange. Why did it output 2 op-ops? Fuck, because this is an expression statement too. That's why. So one of them is for the condition. Okay, that makes sense. Its origin is the compilation of no dog consequence. What? Yeah, actually that doesn't make sense either. Because this is op true, and then there's the jump. Where are they coming from? Its origin is the compilation of no dog consequence. I don't get it. I'm just getting confused now. We do want, I guess it'll make more sense when I implement it. We need to get rid of this op pop because we do want the consequence and the alternative of a conditional to leave a value on the stack. Damn, I am getting confused. That means there should be true 5, 3. Ah, fuck. Okay, I see. I see what you mean. You want to be able to assign the value back if needed. That's probably why there was a pop in the end. Right, that makes sense. Let me look at that diagram again. Let's say this is true. You add and then pop. It's true. You don't jump. You make. Oh. Isn't there a jump missing here? Oh no, actually it's right. Because you can then output this too far. I mean, this started out very good, but now I'm getting confused. What we want here is the 3 and the 2 to be popped off the stack. But the 1 should be kept around so the whole conditional evaluates to 1. So before we tackle our main challenge of given the... Hang on, I missed a bit. Statement. Oh, my mind's turned into mush. Mush. Just getting confused further. Okay. I know it's like it's in the middle of nowhere. I continue tomorrow. Don't know what's going on anymore. Kinda lost. Yeah, plus I've been a bit lazy the last few days. Oh, well, I blame the weather. It's been raining a lot. Okay, I think I'm gonna pause there for now. And then continue tomorrow. Fuck, that was like, that took so many turns. I think it might have been better to try and implement it first. Because now it's just getting me confused. Okay, that's what I'm gonna do tomorrow. I'm gonna just try and build the instructions and then have a look at problems later in the book. Okay, I hope you have a good day and I shall see you back here tomorrow. Yeah, tomorrow. Alright, thank you.